Should I try it one more time, or should we just do it from this part? I'm going to try it one more time. Let's see. Oh, that's good. Okay, so just a quick review of sort of where we've been so far in this class. We started talking about sort of background information, what is chemical engineering. We briefly discussed safety and environment, economics units, and then we spent a while on chemical processes, what they are, how we describe them, how we diagram them, and how we do material balances in order to solve problems about them. Then we talked about fluid flow and mechanical energy balance, and then heat transfer and heat exchangers. So today and Tuesday, we're going to talk about reactor engineering. And then next Thursday will be the exam review. The second exam is coming up. Okay, so about reactions. Reactions are really the main thing that distinguishes chemical engineers from other types of engineers. Now, mechanical engineers study fluid mechanics and heat transfer, but we are the ones who study reactions and reaction behavior, because that's chemistry. That's our expertise. What I have here is a picture of sort of some standard industrial chemical reactors. And over here, to give a different picture, this is a bioreactor growing E. coli, which it is governed by somewhat different equations in some ways, but it is still the same idea. There is still a chemical reaction going on in there that is leading to lots of E. coli. So, by the way, does anyone know why we might want to grow a bunch of E. coli? So E. coli is a pretty easy bacteria to grow. So any sort of bioengineering where you're trying to grow stuff inside bacteria or use the products of a bacteria's metabolism, you can use E. coli. You should look it up. Okay, so when does a chemical reaction happen? So molecules collide. They're flying around, they hit each other, and this collision energy breaks and or forms bonds, and you have new molecules. By the way, so the molecules are flying around and then they hit each other. So what kind of energy is that? Anyone have an idea? Kinetic. I heard kinetic. Are you going to say kinetic also? Yes, so kinetic energy. It comes from their velocity as they're flying around and it suddenly stops as they hit each other. But not all collisions lead to reactions. So for a reaction to happen, it requires them to hit each other with enough force and to hit each other at the right orientation. Sort of an illustration of how that might work. This is ethylene and hydrochloric acid. And at least the current theory is that if the hydrochloric acid approaches that bond in the right direction, then you'll get a reaction. But if it doesn't, you won't. Those obviously aren't the only two options, but that one on the left there, that is the approach that will create a reaction. So, and another way to describe this is activation energy. So most of you should be in chemistry class right now or have taken chemistry before. Does someone want to give me a very brief explanation about activation energy? Hiram. exactly. So Hiram told us that is the energy required for an activation to happen. In this diagram of energy, that is that energy right there that gets you over the hill. So you can go from the higher energy reactants to the lower energy products. So this reaction wants to happen, it wants to go to a lower energy state, but it has to get over that hill first. So what increases reaction rate? Any guesses? Temperatures is one, but yes? Collisions. So it's anything that causes collisions. Temperature causes collisions. Yes, greater pressure. Any other thoughts? Catalysts. Yes?
More surface area.
More surface area for a catalyst or some other situations. Concentrations. That was the last one I was looking for. So yes, so anything that makes collisions more likely or more energetic, so the reactant concentrations. The reactants are obviously more likely to hit each other if there's more of them in the space. Temperature, they're running around faster, so they're more likely to hit each other, and they hit each other with more energy. Pressure, especially for gas. Pressure is, in a gas, is defined as sort of how often and how hard all of the molecules are hitting each other. But, so, obviously, if we want to make a reaction go faster, which we often will want to do in our factories, we might want to put the temperature and the pressure high, but there are disadvantages of that. Thoughts on what the disadvantages of high temperatures and pressures might be? Yes?
You could denature the molecules, or if it's biological, I guess, you could denature the proteins.
Okay, he said you could, in, for example, a biological reaction, you could denature proteins. What that, I would expand on that to say the temperature you need for one reaction in there might be bad for something else you have in your stream. Yes?
Oh, it just costs more.
It just costs more. Yes?
It could explode.
It could explode. It could explode. High temperatures and high pressures. Those explode. Those are just inherently less safe. And so you touched on the things I had here that I had planned for you to say, and then you said them. They're good. Yes. High temperatures and pressures, you usually need more expensive equipment to reach those, and just your operating costs are higher as you go along, and they're inherently less safe. And so, it might be nice to be able to speed up a reaction without having to go to such high temperatures and pressures, which you can do with a catalyst. Okay, catalysts lower activation energy, like so. And generally what happens is that reactants bind to the catalyst surface. The catalyst holds reactants in a way that makes reaction easier, sometimes alters them. This allows lower temperatures and pressures. Okay. I just wanted to include one example of a catalyst. So this is for the reaction of carbon monoxide and oxygen over platinum. Do I have someone who really likes cars and knows what goes on in them? Who can tell me where in a car they use a catalyst? The catalytic converter. I hear from several people. You had your hand up. What does a catalytic converter do?
I don't know much about cars, but I do that for what happens.
Okay, all right. So the catalytic converter, does anyone know and want to say what a catalytic converter does? Yes?
It basically takes all of the nasty stuff that comes out of engine exhaust and makes it less nasty for the environment.
Yes, it makes it less nasty, not necessarily unnasty, but less nasty. So for example, carbon monoxide will react with oxygen, turn into carbon dioxide. We don't necessarily love emitting carbon dioxide into the air, but it's a lot better than carbon monoxide, which is the thing that poisons people when you have gas leaks. Okay. Okay. So the way this particular reaction works with this platinum catalyst is, so the black here is my carbon, the red is my oxygen. So my carbon dioxide and my oxygen both bind to this catalyst surface. The catalyst also pulls the two oxygens apart, which is nice, because then they much more easily attach to the carbons and form carbon dioxide, which then leaves. Yeah, that's good. And there's lots of other examples of catalysts in life. How about somebody who likes biology and knows things about biology? Is there someone who can tell me what we call catalysts in biological systems? Yes. Enzymes. At least two people said enzymes. And there's various enzymes in the body that catalyze the reactions that take place. Yes?
Is there a reverse reaction happening at the same time? With the catalyst?
Probably. There's almost always a reverse reaction happening all the time. But no. I don't know exactly how strong the reverse reaction is there. But yes, so pretty much with almost any chemical reaction, there's always a chance that your products that you formed are going to hit each other and turn back into the reactants. So you almost always have some reverse reaction happening as well. Okay, and we calculate reaction rate using rate laws. And this, what we're going to do today, is going to teach you how to set up some simple rate laws, which you will then use next week when we learn about how we actually design a reactor. Okay, so this is for reactions of, so this is for if it's A plus B goes to C plus D, but in this case, A plus B, that could be any reactants. It could be A plus B plus C plus D plus E goes to whatever. Anyway, just remember A and B reactants, C and D products. This is also only for a liquid. Later on in your life, you will learn how to set up rate laws for different systems. And this is also for irreversible reactions. Speaking of reverse reactions. Okay, so I do want you to remember that those are the constraints which we use when we set up what I'm about to show you, which is this guy. Just to discuss different terms here, we have this rate of reaction, this reaction rate, which is in units of moles per time volume. And then you have a reaction rate constant, the concentrations of your reactants. And these numbers up there are what's called the reaction order. So for example, if N is 2, we would say this reaction is second order with respect to A. And if M was 3, we would say this reaction is third order with respect to B. So that's the nomenclature there. Right, so let's circle back and think about those things we said near the beginning that can speed a reaction up. Do you see where those things are in this equation? concentrations. Okay, so that was one of the things we talked about. Was that, were you going to say concentrations? Okay, so that's one of the things we talked about, and that's in there, obviously. But what about temperature? Where's that? It's in the rate constant. The rate constant changes with temperature. It also changes with activation energy. So, okay, so that's where that is captured. Okay, so now we have, I'm going to give you about, let's say about 8 minutes. Get to 9:35 to work on this example. What we have here is a reaction of ethylene glycol and sodium bicarbonate. We're going to consider it irreversible and first order. I've given you what the reaction rate constant is at that temperature. And the concentrations and the volume. And I want you to get that reaction rate in units of gram moles per liter hour. Okay. Okay. Raise your hand if you're done. Alright, still a couple people. I'm going to give a couple minutes. Okay. Alright. All right. So let's think about this. We want the reaction rate. So we're going to set up a rate law equation. And what is that rate law equation going to be for this reaction? In symbols. Rate of reaction. Okay, K times concentration of ethylene chlorohydrin. And what's the exponent on that going to be? 1. It's first order. And then concentration of sodium bicarbonate. What's the exponent of that going to be? 1. It's first order. And it's irreversible. We can use this. Okay. Okay. Yeah. It's essentially irreversible. But yes, if this was a reversible reaction, we'd need to add other terms, and the book does go into more detail on that if you work through this. Okay, and so, and our units are pretty friendly here actually. What did y'all get?
3.3.
3.3. Raise your hand if you got 3.3. Cool. And that'll be 3.3 liters gram mole hour. And just to check this. Yep, our units work. Okay. Yes. What's happening?
So if, my
Oh,
question first.
sorry. It's 3.3 gram mole per liter hour, which I flipped in my brain. Okay, that is the correct units there. Okay, yes.
So, in the slide picture before, you told us that the rate of action was mole over time.
Yeah. Moles times volume. Moles, gram moles over time, hour, volume liters. So, yes.
My question was, what would happen to the problem if one of the temperatures is different?
One of the temperatures, so,
Because we're given one at 82 degrees and then both at 82 degrees.
okay. So if the temperature of, so I gave you the reaction rate constant at 82 degrees Celsius. If this reaction was not taking place at that temperature, you would need to look up and find how to convert into the reaction rate at that temperature. Okay. Yes?
So say there were two streams of different temperatures mixing together,
Mhm.
you just use the reaction rate of the average of those two temperatures.
So if they're mixing together, we'll get into this a bit more on Tuesday when we talk about reactors, but we usually assume that the reactor it's going into is well mixed so that they will all be the same temperature when they're mixed together. And that temperature might well be a different temperature than both of the streams, especially if the reaction has a heated reaction, right? Or, and so we need to, and so it will produce heat as it reacts, which will change the temperature in there. Okay. So, what would happen if we took this, that 3.3 gram moles per liter hour, and we multiplied it by the volume of our reactor, which is 18 liters. What happens then? Again, you get moles per hour. Okay, we've seen those units before, right? we've seen them before with a kind of reaction rate. Where have we seen those units before? Okay, everyone is whispering. I want someone to say it boldly. Yes. Yes, or it's the units of molar flow rate. And so when we did, if we did a mole balance on this, and we did it on, let's say, on ethylene glycol, and we assume that nothing's coming in, then it would be rate of formation, ethylene glycol, is equal to n dot ethylene glycol out. And what's that rate of formation? It's just this, whatever that was. Yeah, gram moles per hour. So you can see it's all circling back on itself. It's all coming back around. Okay, and you could also find the rate of consumption of ethylene chlorohydrin and the rate of consumption of sodium bicarbonate. And this could go into mole balances like we did so long ago. And then how is all of this related to what we learned about heat transfer? Okay. Yes?
Your heat transfer, how much of the heat flows out of the reactor while the reaction is happening?
Yes, exactly. There might be a positive heat of reaction. We need to remove heat to keep it at the same temperature. What if it is an endothermic reaction and we need to put heat in? What would we need to do then? Yes, Gabe?
You would need to have some sort of heating unit for it.
Some sort of heating unit, a heat exchanger like we talked about on Tuesday, put heat in. Yes?
So in this particular problem, as it started reacting, wouldn't the concentration go down and so?
Again, we will talk about this on tomorrow, but there's a few different, okay, I'll just go very briefly, we have some time. There's a few different kinds of reactor, and it depends. One of them, a very common kind, called it, which you will be using in your lab, called a continuously stirred tank reactor, or a CSTR. Okay, and you have a little glaze, and you mix it up. And so you have your stream going in, maybe a couple ones, but it's mixed up inside, and so we assume that all of everything inside there is uniform because it's being mixed so well. Okay, and so we'll assume temperature and concentration and everything there is constant. And then it will have some output, and we'll just assume that the concentration out there is the same concentration through the whole reactor. But there's other kinds as well. So for example, there's some kind where you have a packed bed reactor and it's sort of a tube and it's full of catalyst, and you send it through this way. And so the concentration of your reactants is going to be high at the beginning and low at the end. Okay. So, all right, and so we talked about how the heat transfer is related to this, material balances. How about fluid flow? How do you think fluid flow is related to this situation right here, where we have this reaction happening in a big reactor? Yes?
With the bottom equation, how you have the reaction rate times the volume, then if we were to like increase the volumetric flow rate, we would increase the like rate of production.
So the volume in there is the volume of the reactor vessel, so that doesn't change with the volumetric flow rate. But the flow rate coming in could obviously change your concentration because it would be carrying reactants and products in and out at different speeds. Yes?
You gotta get it there.
Yeah, you gotta get it there somehow. What kind of machinery would we use to get it there? Pumps. I love pumps. You've had 2 labs where you use pumps so far, so you're beginning to learn. Right. So we might actually get out a little early today, but what I want you to do for about 5 minutes, let's say, and then I will let you go, is we went over a lot of sort of conceptual things today, so I would like you to turn to your neighbor and explain to them these things.
Tests.
As soon as they're graded, I will send you an email and you can come by my office to get
She says she has a few of the proposals done. It was pretty and that's where all the software is.